Hi, welcome to Mathematics with Tom. I am Tom, and I'd like to try one more example of finding an eigenvalue and an eigenvector. And I'd like to take a look at the matrix Q. And this was the rotation matrix, and it was cosine of theta, sine of theta, and minus sine theta, cosine theta. Okay, and what we're going to do is we're going to let theta equal 90 degrees. So the Q that we're specifically working is the cosine of 90, that's 0. Sine of 90 is 1. Minus the sine of 90 is minus 1. And cosine of 90 again is 0. So what does this do? This means that if I have some... Here, I'll just make a quick sketch of a set of axes. What this means is that if I have some vector, it doesn't matter what the length of that vector is. We'll call that the vector x. And if I multiply that vector by q, it means that that vector is going to go to, if I get this about right about there. That is the vector qx. And so my question for you is what are eigenvalues and eigenvectors of Q. Now, before we launch into just running through the process, let's think about this. Remember what we said normally is that we said that if we had some kind of a green vector, maybe, and we had like this vector here, y. So this is y. What we said is if we had some matrix A, and we had a nice orange line here, is that if I was to draw this, then what I would have is this. This line right here is the result of A times y, which is just some scalar of y. So, but notice that if A has eigenvalues and A has eigenvectors, they'd stay on that line. If we say here, we should say y is an eigenvector, then ay equals lambda y. Well, that's this result here. It's this orange line, just some scalar multiple of y. Okay, so it could make the line longer in the same direction, or it could make the line longer in the opposite direction. Now, what kind of a vector, if you multiply it by a rotation matrix of 90 degrees, is going to just stay on itself? What kind of a vector is going to stay on itself? The only thing I can think of immediately is 0, but we said that 0 is not interesting, and 0 is not even an eigenvector. So my logic is failing me. Let's see how the math describes that. So here we go. We're going to do this a little faster. Remember what we said last time. So I'm going to put Q over here. So here's my Q. 0, 1, minus 1, 0 let's try it this way. Instead of using the determinant method, which we did in our last video, let's remember this. We also said that you can find the eigenvalues by lambda squared minus the trace of q times lambda plus the determinant of q equals 0. All right, well, let's try that. So in this case, we're going to have a lambda squared minus, well, the trace is just 0, so that's 0 lambda. Remember, the trace is the sum of the diagonal elements. And then what else do we have? Oh, the determinant of q, that's going to be 0 minus -1, that's going to be a +1 equals 0. And there, what we have to do is we have to solve lambda squared plus 1 equals 0. Now, it may be a while since you've dealt with a solution such as this, but the answers to this is that lambda is equal to plus or minus I. Yeah, that's right. I is the scalar in this case. And so we're actually going to just take a moment. Let's see if we can work with this. Well, what we have to solve is we have to solve q minus lambda I times some vector x equals 0. So this is going to be a 0. We'll use, so we'll do lambda equals I. Well, that's going to be 0 minus, it's going to be a 0. I'll write it this way. 0 minus I minus 1. 1, and then 0 minus I. So this is the matrix of minus I minus 1, 1 minus I. Now this might feel strange. If you recall, I said that you know you're on the right track if this is dependent. If these are dependent. Now, looking at this, it's not so obvious. And usually what happens is when you have an I in here, the multiplier between the rows has something to do with I. In this case, it looks like if I multiply column 1 by a negative I, by negative I would get column 2. So it is a singular matrix. It's just not easy to see. But let's row reduce this. So let's take a row 2, and we're going to add I times row 1. Okay, this is going to give me a minus I minus 1. Then we're going to get, I think I wanted a minus I in there, huh? Well, because I times I, yeah, that should be a minus I. I'll just fix that. So this is a minus I. So then I have, let's see. So that becomes a 1, and then a minus I times a minus I is a plus I squared, which is a minus 1. That's 0. And then I have a minus I plus an I. That's a 0. There's our suspicion. And look at what this tells us. This says now that minus I times x1 equals 1x2. Let's multiply by both sides by an I. So if I do that, multiply both sides by I, then I have I times I, that's going to give me 1. Minus I times I is going to give me 1. So I have x1 and time equals I times x2. And we can see that x2 is free. So our null solution, our xn in this case, is going to be an x2 times I1. And that's pretty simple, so we're just going to say then that our x1, our eigenvector that goes with the eigenvalue of I is I1. So you can even have eigenvalues and eigenvectors that have imaginary components. Hope that helps. Thanks for watching.